So in this lesson, we're going to look at electrical power and connect to the idea of power from back in the unit we did on energy. So quick reminder, power is the rate that energy is transferred from one form to another. So energy is transferred all over the place. You buy energy in the form of gasoline. You store it in your car. That is chemical potential energy. And your engine turns that chemical energy into kinetic energy, and the rate at which the energy is transformed is the power of your engine. And we can measure that power in either watts or in horsepower. So power is the rate that energy is transferred from one form to another. So if my engine can transfer 30,000 joules of energy in 30 seconds, then we would say that it's transferring energy at a rate of 1,000 joules per second, okay, or 1,000 watts. So you may remember from back in Unit 3, the power was the work, we call this work or the energy transferred divided by the time. So anytime energy is transferred, which it is often in electrical circuits, the power is the energy that's transferred divided by how long it takes to transfer that energy. Okay? All right, so if we had energy divided by charge, and we multiply that by charge divided by time, then you can tell here that the charges would cancel and you'd be left with energy per unit of time, which is power. So what is energy per charge? That's one of the things we've covered this unit so far. Energy per charge is just voltage. It's the amount of energy a group of charges has divided by the number of charges. So this is voltage. How much charge goes by in a given unit of time, we just did. That's current. And so we can see that if you take a voltage, which is energy per charge, and you multiply it by a current, which is charge per time, you end up with an energy per unit of time, which is power. And so this is how we find the power in electrical circuits. You take the voltage times the current, and you'll get the power. We sometimes write it as V times I equals P, the power. So here's a handy thing to put in your toolbox. The power in an electrical circuit is the current times the voltage. And we've covered both those things so far. So the current is the flow of the electrons, how many electrons or how much charge is flowing per unit of time. The voltage is the kind of the push on the electrons, making them go. It's their energy per charge. And the product of the two is the power, which is measured in watts, which is also joules per second. Okay, so pause the video if you need to get that jotted down. That's going to be our big equation. So here's a quick example. Your MacBook charger delivers about 4.5 amps or 4.5 coulombs per second of charge to your computer at a voltage of 14.5 volts. So that's 14.5 joules for every coulomb. So it's delivering 4.5 coulombs per second, and those charges have an energy of 14.5 volts for every coulomb. So what is the power of the charger? And also, let's calculate how much energy it gains over the 45 minutes it takes to charge my computer. Okay, so first of all, we're going to draw a little schematic here. When we draw circuits, we draw this as a source of power. So it's two little parallel lines that are of unequal length. And this is called a load. So anything that gets the energy, this is where the energy is going. So this would be the source of the power. This would be your computer, for example. We know the voltage, we know the current, and we know the time it takes is 45 minutes, which is 2,700 seconds. So the first thing we're going to do is we're going to evaluate P equals I times V to find the power, because the first question says, what is the power of the charger? So that's not terribly difficult. 4.5 amps or 4.5 coulombs per second times 14.5 joules per coulomb gives you 65 joules per second, or 65 watts. So we have a 65 watt charger. That's the charger you guys have when you got your MacBook. About 65 watts or 65 joules per second. Okay. Secondly, we know the power always equals the energy transferred divided by the time. So if we know the power and we know the time, we can figure out how much energy was transferred, which was the second part of the question. Okay, so we're going to solve this to find the energy. So the energy is going to be the power times the time. So 65 watts or 65 joules every second times 2,700 seconds gives you 176,000 joules. So that's how much energy your MacBook stores when it charges. So there you go. That's an example problem. And this example problem is also saved for you and linked on the homework. Now, when we buy energy, we buy electrical energy, and you can go outside your house and check out your meter and see. They measure it in a very goofy unit. So let's just talk about that for a second because that connects to a lot of things we look at. Power is energy divided by time, which means that energy is power times time. This sort of makes sense. Power is joules per second, and time is seconds. So joules per second times second will tell you how many joules of energy you have. So one way that you can measure energy is in units of power times time. So a watt second is just a goofy way to measure a joule because a watt is a joule per second. So if you had a joule per second times a second, you'd get a joule. So a watt second is a unit of energy, not power. So the utility tells us energy in a unit that looks like this. It's called a kilowatt hour. Kilowatt is a unit of power, hour is a unit of time, and that's actually a unit of energy. Okay? So when we buy energy, we get charged based on how many kilowatt hours of energy we use, and that's a unit of energy. So here's a handy conversion. 1 kilowatt hour, a kilowatt is 1,000 watts, and an hour is 3,600 seconds. So a kilowatt hour is actually 3.6 million joules. All right, so we're going to use this as a conversion factor. If your house in a given day uses 75 kilowatt hours, then you can figure out 75 kilowatt hours will be 3.6 times 10 to the 6 joules times 75. So we're going to use this as a conversion factor. I've got an example coming up of that. Okay. So here's my example that kind of puts this all together. I've got a water heater. It's electrical. It draws 10 amps of current at 240 volts. So my water heater is actually on a separate circuit from the rest of my house that has a higher voltage. So 10 amps is the current and 240 volts, that's 240 joules for every coulomb of charge. It takes 20 minutes to heat the 50 gallons of water that are in the tank. And I want to know, what is the power of the water heater? How much energy does it use? And what will it cost to heat up that tank if electrical energy is 11 cents per kilowatt hour? So each kilowatt hour of energy I use, each 3.6 million joules of energy that I use, costs me 11 cents. That's about what Duke Energy charges here in Indiana. All right, so we're just going to draw a simple little circuit and list the things we know. We know the voltage and the current. We know the time, and we're looking for the power. So we're going to find the power by taking the current times the voltage. So the current, of course, is 10 amps. The voltage is 240 volts. So that tells us that this is a 2,400 watt heater. All right, that's the rate that energy is being transferred from electrical energy, which you're paying for, to heat energy. The second thing we want to do is find out how much energy. Well, if you're using 2,400 joules of energy every second, and you do that for 20 minutes, you can figure out that the energy you're going to use is going to be the power times the time. So we're going to solve this for the energy. So the energy is going to be the power times the time. So 2,400 joules every second times 1,200 seconds gives you 2.88 million joules. So it takes 2.88 million joules of energy to heat my water. Okay. All right. Lastly, we've got to figure out, what does that cost? So we used 2.88 million joules. And we know that each 3.6 million joules, because that's what a kilowatt hour is, each 3.6 million joules costs 11 cents. So we don't have quite 3.6 million joules, so it's going to be a little less than 11 cents. So we're just going to set this up as a conversion factor, okay? So we're going to start with our 2.88 million joules. 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules, so that's a conversion factor. And I need the joules on the denominator because it needs to cancel those joules in the numerator. So those will cancel and leave me with kilowatt hours. And then 1 kilowatt hour is equivalent to 11 cents. So I can make this a conversion factor also. That way the kilowatt hours in the numerator cancels the kilowatt hours in the denominator, and I'm left with dollars. And then when you run the numbers through there, you get 0.09 dollars or 9 cents. So it costs 9 cents for my water heater to heat up the water once using electricity here in Indiana. Okay, So that's what we're working on. The big idea here is the power is equal to the current times the voltage, and the power tells you the rate that energy is transferred. So once you know the power, that's going to be the energy divided by time. You can solve for the energy or the time if you need to. And then the second thing we learned was that a kilowatt hour is a way to measure energy, not power. So once you know the energy, you can use this conversion to figure out how much energy costs. Okay? All right, you've got some problems to solve in the problem set.